Sorry. Now it's up.
Oh, yeah.
It's okay.
Yeah. Then I have to say yes. Okay? This is for you. So please remember, like, maybe 20, 30 years later, you might say, well, 30 years ago, this guy came and he was rather excited about recipe 10 galaxies and so on. But now, 30 years later, you might be talking about, I don't know, let's say 50 or let's say 100 supernovae and galaxies and so on. So this is for you. Somebody please inherit this and then use this for your future talk. Okay? What is the current status? Yeah, sometimes this happens. See, sometimes this happens. The time stops. I really don't know. Yeah, sometimes. And then it's not. Next one is a nice picture showing the distant AGN, but only I can see that. Oh well, what happened? Okay, this is not the end of my talk. This is.
Your video is working on Zoom.
Yeah, how can I, let's see. I can't even escape from, there we go. Sometimes this pointer is very moody. Anyway, this is the recent picture from brand new James Webb. We see, this is a galaxy cluster and then a huge gravitational lensing. And then we see behind that galaxy cluster, we see about, let's say, 10 galaxies here containing a massive black hole of 10 to the 8 solar masses. So this is super exciting with James Webb Space Telescope. And the most surprising thing to me was like JWST, like everything is working perfectly. There was a small problem with MIRI, but then we find nice superb pictures even compared to like Spitzer or other space telescopes. And then we discover this distant object. Okay. So this is one of the recent development. The other one is also interesting. It's actually a nearby object, relatively nearby within our Milky Way galaxy. So this particular star, Lamos J1010 or so, this is a stellar relic. What is that? This is a high-resolution spectrum of this star with the small ion content. So this is a typical metal star with ion content of -2.4 or so. But if we compare this spectrum with the other one, the blue line, with a similar ion content, similar metallicity, but then you notice this Lamos star has a very small like sodium content, magnesium, and so on. So this is like iron per metal cluster, but also like alpha element is like it's deficient with alpha element. If we plot the elemental abundance patterns of this star like this, it's very peculiar. You immediately these red points are the observed data, the elemental abundance pattern, and compared with the theory modeling. So this star has a peculiar abundance. It's obvious if we plot this calcium over silicon or magnesium over silicon in this way. It's here. And unlike other stars, other similar stars, this is located to a little bit offset from this majority. Okay, we see this strong odd-even pattern in this abundance elements and very low alpha elements abundance. These are not really produced by core collapse supernovae. I explain a little bit of physics. So think about the evolution of a very massive star, very massive meaning beyond the 100 solar mass or so. Okay, so the core temperature, this is core temperature and the core density. Core temperature density evolution goes on the high temperature track. The center is essentially radiation dominated on the high temperature. At some point, it enters to the so-called pair instability regime, where the temperature is large enough so the two photons generate the electron-positron pair. Okay, since this happens at much lower densities compared to the core collapse supernova explosions, the so-called neutronization reactions, like converting ion to manga and so on, this doesn't happen really. Okay. This produces, so neutronization typically smoothes out this the odd even patterns. But if the explosion happens at very low densities, like in pair instability supernova, then it preserves this strong odd even pattern, just like we see here. Okay, this means that Lamos star is a remnant, or that star is like second generation star that was formed out of the material produced by the explosion of a 260 solar mass, a gigantic star. This is the almost a direct signature of a putative pair instability supernova in the early universe. Okay, so I talked about massive black holes in the distant universe, and also I showed a metal cluster in the relatively nearby, like in our neighborhood. So these seemingly very different two objects. This is something I like with astronomy. These seemingly very different objects, they may have a common origin, and that origin might be also related to ourselves. Like, our body consists of carbon and oxygen and so on. These elements were produced at some point in stars, and they were like ejected, and then after many generations, we are here as ordinary materials. Okay, so the topic of first stars is interestingly at the junction of many interesting topics, say from dark matter, nucleosynthesis, metal clusters, black holes, black hole binaries, galactic archaeologies, reionization, and so on, even gravitational waves. Everything began from this state. Now, in the beginning, as you know, in the early universe, the state was very simple. It's just a sea of light elements and dark matter and tiny density fluctuation, just ripples left over from the Big Bang. And afterwards, from this simple state, gravity drives the structure formation, just like in this way. So this is a nice movie from one of my simulations. So starting from this diffuse state, gravity drives the development of this complex structure, like this typical filamentary knots or the void-like structures like this. By now, there are many so-called mini halos. Mini halos merge together to form the first galaxy-sized object, like this. Like this. Okay. So when the first stars were formed, the things were still relatively simple. You can imagine that just like this picture. There's a gas, diffuse gas consisting of hydrogen and helium, and maybe a trace amount of hydrogen molecules, and that's it. And the gas is like pushed by its gravity, by self-gravity, or by that of dark matter. And the slow radiative cooling by H2 molecules make it happen to cool and condense. Okay? It needs to go all the way to the stellar densities, and the physics are a little bit more complicated from a diffuse gas to really a compact and dense star. There are a number of chemistry and radiative transfer and dynamical things and so on. This shows the typical thermal evolution of a primordial gas from a cosmic diffuse gas to stellar density. Okay, but this complexity is not the main concern of my talk today. Okay. Now, the computers are powerful enough to really simulate these physics and then to form the primordial stars in the large enough cosmological volume. So this picture shows some of the examples that we found in one of our simulations. They're forming these massive stars. For a few reasons, we think that the early universe provided the ideal conditions for massive star formation. First, because of the lack of efficient coolant, the gas remains relatively hot. It's like high temperature gas cloud. And because of that, the corresponding gene's mass is very large, about 500 solar masses. So this is the mass available for star formation. And because of the high temperature, the gas mass accretion rate onto the protostellar object is also high. It scales with temperature to 1.5 or so. Compared to the present day universe, the typical mass accretion rate is about 0.01 solar mass per year. So if you multiply by 1,000 years, you can easily get 10 solar masses. And also there's no dust grains or no metal, so usual radiative feedback doesn't really operate. So this is what I say the kind of ideal conditions to produce massive stars. Okay. So this is simulation result showing the mass distribution of fast stars from computer simulations. Okay, spanning a wide range from 10 to all the way to 1,000 solar mass. And I wouldn't even say this is a prediction, but this is a numerical result. And then, now I'm brave enough to compare this distribution with the observationally inferred mass distribution like this. So here I use 5 or 6 metal protostars and inferred mass distribution of their progenitor supernova explosions, just like I did in the beginning. Okay. The beginning example was this, pointing to 260 or so. The observations still not enough statistics, but at least this wide variety is consistent with what we find from numerical simulations. Another interesting thing is the high mass end. These very massive stars, their fate is collapsing to leave remnant black holes with roughly the corresponding mass. So there might be, this might be also a good way of producing, leaving a very massive, massive stellar mass black holes. Okay. Let me skip this. This might be related to the gravitational wave sources recently we directly observed. For that, we need binaries. And then let me show you one nice example of the simulation of binary POP3 star formation done by Katsugi. Okay, now I show a movie. The movie shows the sequence similarly from the gas cloud to protostellar formation and then the binary formation, just like this, starting from gas cloud. Now it's 30,000 AU, so we are progressively zooming in onto the central part, down to 10 AU or so. So these spiral arms fragment to produce these two main protostars with a wider separation, actually, not very close binaries. And now one star is now ignited. This a dipole shape is like H2 regions, the ionizing photons like this. And these two stars shining but interacting dynamically and keeping this binary configuration. Okay, for now, at the moment of formation, they are like wide binary. But if there is some other dynamic mechanism, they might get closer and merge within the cosmic time. So nicely, we have a good hope. The Cosmic Explorer is the US proposed third generation gravitational wave observatories. It's like roughly 10 times bigger than the LIGO. And then it has about 30 or 50 times better sensitivity. So currently the LIGO or gravitational wave detectors, they have a sensitivity to observe black hole mergers below redshift 1 or so. But once this Cosmic Explorer begins operation, then we can see these mergers everywhere in the universe, all the way beyond redshift 10 and even like close to redshift 100. So this is spectacular. Anywhere in the universe, when these black holes merge, then it sees or it hears its sound as gravitational waves. Okay. Now, so far so good, interesting enough, but I missed one important piece of information that here the cosmology enters. So one important physics imprinted in the early universe is this baryon acoustic oscillation. In the early universe, there is a gravitational potential by dark matter, and the baryons, photon baryon fluids was moving within this potential, generating characteristic acoustic motions in this. And then that's something we directly observe as cosmic microwave background. Okay. Typically, this generates the supersonic gas motions with respect to dark matter. Okay. So this is showing the calculated density structure of 500 megaparsec and the corresponding velocity structure. So these are at redshift, I forgot, maybe 20, yes, redshift 20. The relative motions velocity is like a few kilometers per second. This is way too higher than the thermal velocity, the sound velocities at that time. So there must have been this large and fast motion of the gas with respect to dark matter. And this causes very interesting effect on the star formation. Okay, depending on the strength of this wind. So in some regions, there's strong wind, a very windy region. It typically generates a very turbulent gas cloud like this. And in an extreme case, that gas cloud produces like 10 to the 4, 10 to the 5 solar mass star at redshift 30 or so. Weak wind regions, typically we find filamentary structure or star cluster type things with 10 solar mass stars or so. This might be also a source of massive black hole binaries. And little wind case, that is something we explored 10 years ago as ordinary case, without the effect of these streaming motions. We saw this mass distribution. Okay. Another interesting thing is we usually think this structure formation driven by the dark matter gravity, but because of these relative motions, there are sometimes gas clouds offset from the dark matter center. So this is one example by Anna Schauer. We notice this gas motion from left to right, and it displaces the gas clouds positions with respect to dark matter. Another example has been done by one of our students at University of Tokyo, Nakazato et al. They showed, compared to the dark matter density, the gas density looks like this with streaming motions. And then we see this filamentary structure is slightly offset compared to the underlying dark matter. Underlying dark matter distribution is shown by the pink contours. And finally, by redshift 21 or so, this a gas cloud completely offset from the dark matter halo once produced. We follow this further evolution, and then we find this gas cloud becomes Jeans unstable by self-gravity when its mass is about 5 times 10 to the 4 solar masses. So this is one interesting way of producing star or star clusters with this size. Okay. And then we also find, more recently, we also find a more extreme case of forming many stars at once. And this is an example released last week from UCLA showing, bright small galaxies can be formed without the help of dark matter. This can be an interesting test of all this structure formation paradigm. So please see this impressive press release from UCLA. Okay. Now, because of these relative motions, the density distribution of the gas is slightly different from what we thought before. And then additional effect arises, as pointed out by a few authors. Okay. So because of this relative density perturbations and offset and so on, the gas density fluctuation, the temperature fluctuations are slightly misaligned. Well, this is a slight effect, but if we care about the magnetic field generation, this is super interesting because this is the typical induction equation with the so-called battery term. So when the density gradient and the temperature gradient or their respective distributions are different or misaligned, then there is a battery effect generating a slight amount of magnetic field without invoking any exotic way in the early universe. Okay? So according to the calculation by Smadar-Naos and Ramesh Narayan, the produced magnetic field strength is up to 10 to the minus 25 or minus 24 Gauss at very early epochs, like let's say 30 or 100. So this gives a natural way of seeding the magnetic field, even at such an early epoch, without really anything invoked, say, phase transitions and some exotic physics in the early universe. Okay, so I need to modify slightly this simple picture of a primordial gas. Very likely, this primordial gas was at least weakly magnetized because of that effect. And then I run by myself the MHD simulation starting from these realistic initial conditions, and then I found the development of large-scale magnetic field in this way. Large-scale here means like a 1 megaparsec box or so. So it roughly really traces the gas density distribution just like this. And interestingly, the magnetic field orientation is also like along this filament or so. And at this point, around let's say 17, the maximum field strength is 10 to the minus 18 Gauss. It's dynamically completely unimportant. But this is still like a seed. So things beyond that, I need to do kind of analytic or subgrid modeling, because even though I use adaptive or moving mesh simulations, typically the gas motions or microscopic structure of the gas is not really resolved. So here I resort to using the subgrid model of turbulent development and associated kinematic magnetic field generations following the prescription of these, starting from classic paper by Kazantsev, Karlsruhe, and more recently Lazari and Chris-McKee and so on. So the essence is for a given power or turbulent structure, the small scale dynamo begins from the smaller scales and eventually convert these kinetic motions to the magnetic field energies. And the energy increase rate is given by this, by characteristic length scale and velocity, like circular motions of the smallest eddies, and it's literally exponential. So if I implement this energy equation in the individual cell, I get this. Well, this is kind of a, what's it, like exciting, but kind of disappointing, because in the end, it's like after this good effort of estimating the magnetic field generation, the answer is like, it's like yes or no questions. Once the small scale dynamo sets in, and then the increase is literally exponential. Even if we start from a very tiny seed of 10 to the minus 18 or so, it quickly goes up to the 10 to the minus 6 Gauss, micro Gauss or so. And here I show the development as a function of the gas density in linear scale. So you now realize, appreciate this exponential growth in this way. So, so this suggests very likely, starting from this tiny density fluctuations and tiny magnetic field seed, it ends up with a significant magnetization of primordial gas cloud. Okay? By the way, this calculation itself result is consistent with the result of recent paper by Chris-McKee and his colleagues. Okay, what is the matter? The most interesting thing, perhaps, is its effect on the say evolution of the primordial gas or disk or multiplicity of stars and so on. So here I show the simulation of by Sharda et al. Just comparing as by a parameterization, starting from no magnetic field or like with a small amount of initial magnetic field, the same object evolved in very differently. The zero magnetic field case shows a typical fragmentation and star cluster formation, but with this slight amount of magnetic field, it produces in this case only two and forming this binary thing. And so obviously, they according to their parameterized study, this initial magnetic field really changes the multiplicity and the stellar mass distribution, as shown here. This is like their sync particle protostellar mass distribution from 1 to 10 solar mass. It's shifted toward a high mass end by adding the magnetic field. So this is something, here in this talk, I should say as an open question and something I need to explore more, starting from the realistic initial conditions that I described. Okay, the final part, let me spend maybe 5 more minutes to discuss the another cosmological issue. Okay. As you know, people many times say the success of the standard model. The standard model means here the lambda CDM. So this shows the mass spectrum, the abundance of massive objects from small galaxies to galaxy clusters, and compared with a variety of observations from CMB, galaxy clusters, galaxy redshift surveys, and Lime alpha forests, and so on. So this impressive agreement between the theory curve and observed data points, this is what people call the success of lambda CDM. This is the establishment of the standard model. Okay? Now, however, the success has been confirmed only down to, say, in mass scale, the galactic scale, 10 to 12 solar masses. Beyond that, subgalactic scales, we don't know how well it is. And we, honestly, we don't know how the primordial power spectrum looked like in the early universe on this galactic scale. This is a similar plot, but in terms of power spectrum, this is a wave number. So all the way from galaxy clusters to, say, galaxies, again, they are observed estimate. This is nicely consistent with the theory prediction. But recent studies, for example, for Milky Way dwarf galaxy structure and strong lensing measurement and so on, it might hint some slight upturn of this primordial power spectrum, essentially suggesting maybe or indicating that the excess power at small galactic scales. This might be very interesting in terms of the recent JWST discovery of more early galaxies than expected before, as emphasized in many different ways. But let me take this case. So if we plot the integrated stellar mass density at redshift 9 and redshift 7.5, the observations points to these green regions. Okay. For now, we believe all these observations, and I know at least 1 or 2 of the galaxies are turned out to be low redshift interloopers. But for now, the excess amount of stars or excess amount of small galaxies are sort of like, it's robust to say that more galaxies than expected. And then we see these, these solid lines are the predictions from the standard model, okay? So obviously, unless we invoke a very exotic mechanism, like very efficient star formation in early dark matter halos or some other stuff, we can't really reconcile this observed abundance. Okay, and there are many other ways to express this sort of overabundance of the early galaxies beyond redshift 10, 12, and so on. Okay, so we do a little bit of a test. So what if the primordial power spectrum has this tilt pointing to more excess power at subgalactic scales? The effect is very dramatic. Okay. So we run the simulations. So this is the structure of the standard model, and at risk 9, we don't really see anything like this. There's only a few objects. If we plot the galaxy abundance, it's more obvious. But if we put a slight or strong tilt, the structure formation accelerated, and we even find like clumpy galaxies already at risk 9. So just like we maybe observe by detect by recent JWST observations. Again, in terms of galaxy abundance, it's clear this slight tilt really affects significantly to the abundance of galaxies at risk 9. Okay? Interestingly, this change or modification does not ruin the success of the lambda CDM at large scales. Compared to these two cases, the present-day large-scale structure of 50 megaparsec, it looks essentially the same thing. If we plot the mass function, it's essentially the same. So only significant change it makes is the abundance of galaxies at redshift 9 or 7.5 and so on, which may be consistent with the the past 1 or 2 years, people are arguing like there are many more galaxies that might be like explained by this modification of the prime order power spectrum. I just finally want to emphasize that we have been exploring this over 10 years already with other people, and then it's not really like after the JWST discovery we rushed into some particular model. It's not like that. We have been exploring this possibility for almost 10 years, and then one nice result is if we allow this tilted power spectrum, the first star formation can begin at even let's say 50 or even 200 under very extreme conditions. And for now, this is like theoretical and something to be tested. But now I come back to my original plot. In the future, we don't know. My young colleagues, you have plenty of time, say 2040, and even like the 22nd century or so. And we can ask, when or how distant were the first cosmological objects, stars, black holes, and supernovae. And now it's all your task to prove and say, or even like, you smile, say 2073, when I celebrate my 100th birthday, saying, well, let's say 10 galaxy was nothing distant, okay? All right, I should conclude my talk. So I talked about physics of primordial star formation and related it to pair instability, massive star explosion, black holes, and the gravitational waves. And I kind of added new physics, early universe physics, ring motions, and associated magnetic field generation and its implications to primordial stars. And finally, I talked about a little bit of cosmology to be proved by high redshift galaxies and stars. That's the end of my talk part. Thank you very much.